Hey students, this is your Professor Chuck, and today I'm going to talk about derivations and introduce them to you. Basically what we're going to be doing is what I call a syntactical approach to logical entailment. Alright, so you might be wondering, well, what do you mean by that? And that's a good question. So instead of answering it directly, what I'm going to do is actually talk about truth tables again, right? And just talk about their advantages and disadvantages, right? Here's the thing about truth tables is that they're very simple, right? They just kind of lay everything out before your eyes, right? You have a nice, binary system. It's either true or false, and then you can kind of mechanically fill things in according to the rules of your language, right? So depending on how the meaning of your terms go, the truth table then just captures each step along the way, and you can mechanically fill things in from the parts to the whole and capture those truth functional meanings. Like I said, it's all before your eyes, meaning you can see everything. It's comprehensive. All of the possible interpretations of your sentences are captured, and that way you can see what everything means in every model and then determine your semantic properties. Very, very handy. Okay. However, as you've worked with them a little bit, especially in your constraint satisfaction problems and working with them in the homework and on the midterm, you found that these things can get pretty big and unwieldy really fast. So you get beyond more than four choices, and this becomes very tedious. All right, 16 rows is pretty big already. You go beyond that, and you're going to start looking for shortcuts, right? And they also can be kind of error prone. If you just maybe if you're like me, sometimes your F's can look like T's, or your T's can look like F's, or you just kind of make a dumb mistake. Maybe you miss a negation, or you just fill something in wrong for whatever reason. And then the whole analysis just falls apart. It's completely flawed at that point, right? And so you can't, they can be kind of unreliable, right? You can't really rely on them. The other thing about truth tables too is that they don't really represent how we reason, at least naturally, right? One of the things that we do as thinkers is we kind of move step by step from things that we know to things that we don't know. And it's nice if we could kind of represent some discovery. With truth tables, this doesn't really happen, okay? Because everything is just sort of comprehensively laid out, and you just have to see it, okay? So if you were going to use a truth table, right, to figure out whether or not this argument is valid, right? You just take a look at that. You cannot break it up into smaller pieces, right? Everything interacts with each other, and so you're going to have to, you got like 6 different atomic formulas here, right? So, and so that's going to make, you got 5 compound formulas too, and that's going to make for a 64-row truth table with 11 columns. All right, and that's just going to be a pain in the butt to figure out whether or not that argument is valid. Okay, and so this is kind of the point of entry. I want to take you on the journey now of derivations. Right, what is a derivation? Okay, well, in the most basic sense, a derivation allows us, it's a tool of analysis that allows us to move from one assertion to another in a stepwise fashion. Right, and what's interesting about that stepwise fashion, right, is that it does so in a truth-preserving way. Remember, truth preservation is really important for the concept of validity, right? You don't want to be moving from truths to falsehoods, okay? And so that's what we want to do in our derivation system. Now, the way we're going to do this is that we are going to follow rules about how to correctly arrange the symbols of TFL, right? So what's interesting about derivations is that you actually don't really need to know the meaning of the symbols. Now, that really helps. It's a lot easier to do these things when you do know the meaning, all right? But the thing is that you don't have to do them. You could actually program a machine to follow certain rules to manipulate the symbols of TFL in a logically valid way, right? And that's what a derivation will do for you. A derivation is going to be a kind of maybe rule set. You follow these rules to manipulate these symbols. And the symbols can only be arranged in certain ways. Okay? So derivations are syntactic in arrangement. I'm sorry, syntactic in nature because they have to do with arrangement. Right? Now, by contrast, truth tables are very semantic in their nature, right? Because you're evaluating the meaning of the sentences, right? You're determining whether they're true or false under a certain model, right? And so that analysis, is kind of nice. It's very intuitive for us because we like the binary system of truth and falsity, right? And we can kind of figure things out that way. And that's what makes derivations challenging, is because they are syntactic in nature, right? These can be very difficult. Students, I find, have a lot of difficulty with derivations because it's just all about rule following. And in order to apply in order to follow the rules, you have to know what the rules say. You have to be able to detect the patterns in which the rules apply. And so you have to have some kind of sensory capacity to see the patterns in which the rules will apply. And this is just really tough. Okay, this is really tough. And so I want to introduce you to the idea, at least, in this lecture, about how to set up a derivation. All right, so here's kind of our traditional argument form that we've been kind of looking at. We got our numbered premises, and then we have a line that separates the premises from the single conclusion, and then the conclusion is marked off here by those three little dots. Okay. When you set up a derivation, okay, you have to kind of think backwards, all right? And this is another thing that makes it hard, right? So down here, the last thing, right, is your conclusion. That's on your last line, all right? When you set up a derivation, you actually want to get the conclusion before your eyes first thing. So you'll have derive Ka, because that's the conclusion. That's what we're aiming for. That's where we want to go. Right now, we're going to need the premises, right? And we got 6 of them here, so we're just going to list those. And it looks a lot like the argument form we've been normally working with, except that now, right, we remove this line, and we have kind of 3 different columns. We have the number line, which we have over here. Then we have the formula column here, right, which we have here. And then we have this marginalia column, right? And that, you have a bunch of P's here, and what that means is that these are all premises, right? P for premise. Now, here's what we have to understand, okay, is that we can get to Ka because we have Fa, right? If you remember the inference of modus ponens, the way that inference works is that if you have P, then you have Q, right? So if P, then Q, that's an assertion. That's premise 1. And then you have P, right? So then you can conclude, therefore, Q, right? So that's a valid argument form. Here's the truth table that proves it. Okay, suppose that P is true and Q is true. I'm sorry, that P is true and P arrow Q is true. Well, then Q is true, right? You're never going to move from 2 truths to a falsehood. That just never happens. Okay? So, what we're going to do here is, at least for the sake of argument, is we're going to assume our premises are true. Now, we might come up with reasons to doubt that assumption later. I'll talk about that. But just for now, just think of this as being true and that being true. And then, therefore, Q is true. All right, so that's modus ponens truth table. And we can actually distill this truth table into a rule of inference, right? So we're gonna capture that here, right? Now, I call this a rule of inference, and this rule of inference has a specific name. We're gonna call it conditional elimination, right? Conditional elimination is signified by this arrow E, right? So when you see this, what does that arrow E mean? It means conditional elimination. All right, so what we're doing here in this rule of inference is we're actually symbolically removing this arrow. Okay, so how are you going to do that? Well, if you have P arrow Q on a line and P on a line, then you're allowed to write down Q, because that's what modus ponens will allow. That's a valid rule of inference. All right, so I call these little things, icons, right? They're the visual representation of the rule of inference. And the way you should understand them is that what's above the line, right? What's above this line right here, right, specifies what well-formed formulas the rule requires to appear on any lines of a derivation before the rule can be applied. Okay, so you got to have these two things. Take those things as input. Then as output, you can write what's below the line, a single well-formed formula written on a subsequent line, and then you would cite the lines that satisfy the requirement. All right, so to kind of get a handle on this, now let's just use this rule, okay? Let's use this rule. All right, here's our problem. We want to derive Ka. All right, now notice here that I have Fa by itself. And if I get Fa by itself, right, I also have an Fa arrow Ga. And if I get Ga, I can get Ha. If I get Ha by itself, I can get Ia. If I have Ia by itself, I can get Ja. And I have Ja by itself, I get Ka. All right, so what I'm going to do, actually, is I'm going to apply the rule of arrow elimination to lines 1 and 2, which allows me to write down Ga. Okay? Now that I have Ga, I can get Ha on line 7. Okay, and notice what's happening here is that I'm citing the two lines in which I got this from. Lines 1 and 2. How did I get it? Arrow elimination. Okay, so Ga is derived from Fa and Fa arrow Ga by the rule of inference called conditional elimination. What lines were Fa and Ga on? 1 and 2. Right, now I'm able to get Ha because now I have Ga. So I derive Ga. That becomes something I can use. Okay, and notice that I have Ga arrow Ha. Here's the Ga, and now I can derive Ha from lines 3 and 7. All right. Now that I got Ha, right, now I can write down Ia because lines 4 and 8. Right, I got Ha on line 8, and I got Ia arrow Ja on line 8. Okay, now that I got Ia, I can get Ja from lines 5 through 9. And again, I'm using arrow elimination here, conditional elimination. And now I can get Ka, because then I have Ja arrow Ka on line 6 and Ja on line 10. So now I can write down Ka, cite lines 6, 10, arrow elimination. Now once we reach Ka, we're on our last line. Okay, we're on our last line. We reach Ka on our last line. We are done. We've derived it. Right. So the last line of your derivation signifies what you've concluded. All right. Okay. So that is the first pass on how derivations work. All right. Now here's some things to note. Basically, what a derivation is, they are ordered and numbered sets of well-formed formulas. Okay, so you think of the idea of an ordered set, right? They come in a certain order, right? The formulas come in a certain order. Some of the formulas may be given as a premise. Others might be assumptions that we make. I'll talk a little bit more about that. And then any others that we add to the set are going to be derived by a rule of inference, like arrow elimination. The last in the set is what is ultimately derived, and that's the conclusion. Okay? All right, so let's talk about derivations with assumptions. All right? I talked about how sometimes we make assumptions in our set of ordered set of formulas. So suppose we're going to derive Fa arrow Ha. And our premises say this: Fa arrow Ga and Ga arrow Ha. Well, what do we do? Okay, what do we do? Well, let's think about it logically, right? That's always the answer, okay? Let's suppose, for the sake of argument, that FA is true. All right, so if FA is true, well then GA is true because we can derive, right, we can derive GA from FA arrow GA and FA. Okay, that's what we were doing in that last slide. We were using arrow elimination, the modus ponens inference. Okay. Now, when we get GA, we can get HA, right? That makes HA true because now we have GA, and then GA leads to HA, so then HA is going to be true. So here's the idea, okay? This is the big idea, and if you're not following me, this is what I want you to pay attention to. Right? We can conclude that if FA is true, then HA is true. Okay? So what we'll do when we do this part right here, supposing that FA is true for the sake of argument, right, what we're going to do is we're going to create a subderivation, which is a derivation inside of a derivation. Okay? So I'm going to assume FA. Now what I do here is I indent, I kind of move to the right, and I draw a line. That's going to signify a subderivation. I've started a derivation inside my derivation. I also use the letter A to indicate to the reader that I have made an assumption. Now within that subderivation, I can make use of my premises. These are accessible to me. My premises are always accessible to you. And so what I'll do is I'll take line 1 and line 3, right, and I'll use my rule arrow elimination, and on line 4 I'll write down GA. Okay, do you see how I got that? That's line 1 and line 3, arrow elimination. Okay, now that I got GA, right, I'm just going to kind of do the same thing. I'm going to reach up here, make use of line 2, and derive HA. Now I am within the scope of this subderivation, right? I haven't stopped this yet. I'm still deriving, I'm doing a derivation inside of a larger derivation, okay? All right, so you might be wondering, okay, well, now what, all right? Well, here's the answer, right? Remember that part that I talked about? If HA can be soundly deduced from FA, which is what I've done in this subderivation, then I can say, well, if FA is true, then HA is true. Okay, and I actually have a rule, right, that allows me to do this. It's actually called conditional introduction. So by contrast, conditional elimination said arrow E, this says arrow I. Here I'm introducing a connective, I'm creating a connective. Now how do I create this, something that looks like this P arrow Q? Well, what I do is I start a subderivation and I assume that P is true, and then try to derive Q. Okay? So the first part of this rule, right above the line, it requires me to do a subderivation showing that I can deduce Q from P, right? Q is what's on the last line of my subderivation, and I get that from my assumption. So once I do that, right, the second part, right, then it does a special action where I stop the subderivation and I move back to the left here. That's called discharging the subderivation. When I stop the subderivation and move back the indent to the left, then I've discharged the subderivation. And then what the rule tells me to do is write down P arrow Q. Okay? So let's go back to the problem, right? I have now been able to derive HA from FA. So what I'm going to do now is I'm going to stop the subderivation, I'm going to discharge it, I'm going to move back to the left, and now I'm going to write FA arrow HA, and the way I'm going to cite this is I'm going to write lines 3 through 5. Notice how I use a little dash right there? That lines 3 through 5, because what that is signifying is the subderivation. That is the subderivation that justifies this, and then I write down arrow I. Okay, so that's how it's done. Feel overwhelmed yet? Okay, all right. If you do, that's okay. All right, no problem. We're gonna move through some very simple practice problems here just to kind of get a hang of using arrow elimination. All right, what I want you to do is basically get the feel for writing down the problem. So what I've done is I've just written down the problem the way you should write it down. Okay, so just write that down. And now what I want you to do is deduce F A. Okay? How in the world are you going to do that? All right, well, let me walk you through it. Okay? What you have here, right, this is where you want to go. All right? This is your target. You should always be thinking about where you want to go and think about how to get there. So before you write anything down here, think about how you're going to get there. Now, where is FA in your premises? Right? If you're looking at your premises, right, FA is right here. That is, look at that. It's a consequent of a conditional that's part of a larger conditional. Okay? So what you have to do, right, is eliminate this arrow, get rid of that part, and then get this by itself, and then eliminate this arrow and get the FA by itself. Okay? So what you're going to be doing in this problem is eliminating for F. Now, the way to do that is you first got to get rid of this arrow. All right? So what you're going to need, right, is you're going to need HA, which you have on line 2, right? So you have those two together, and so you can get rid of this part, and then what you can write down on line 4 is this part, all right? So what you should do then is on line 4, okay, is write down that. Okay, that comes from lines 1 and 2. Use arrow elimination. Okay, now it's easy to get FA. Okay, do you see why? Well, on line 3 you have GA, which is the antecedent of this conditional, right? Arrow elimination, right, allows you then to write down FA, okay, from 3 and 4, all right? All right, here is a more complex one, all right? I want you to drive FA, arrow MA. Now, I only want you to use arrow elimination, okay? Don't worry about using arrow introduction, okay? So what you do is, okay, this is what I want to get. This is what I need on my last line. Now, where is it in my premises? Okay, if you're inspecting your premises, you should see it right here. Okay, so you're going to have to eliminate this arrow. Okay, and you're going to have to eliminate that arrow as well. I know I get kind of loosey-goosey with the way the parentheses go here. All right, so you can get rid of this piece right here because you have LA on line 3. So from lines 2 and 3, you can write down that. All right, now you should be able to see that you can get this piece because you have this piece up here on line 1. So you should write down then line 1 and 4 arrow elimination. Okay? All right, here's one that's here's one that's even more complicated. Okay? Notice that one. So here's your target, FA arrow FA. All right, and you have to use arrow elimination to get this. Okay, how are you going to get that? Well, here's an FA, arrow FA. You could get that. That might work. All right, you could do that. Or you could get it here too. Okay, so let's think about this. All right, let's think about this. You know, the problem is that you don't have an FA by itself anywhere to get this FA. So this FA, arrow FA. Right, so you're gonna probably have to go for this one. Okay. Now here's the thing. Here's the main connective right here. And this is saying, okay, we've got an FA arrow and then a parenthesis. This looks a lot like what's on line 1. You see that? Okay, so if you can eliminate then this arrow and this whole part from lines 1 and 2. All right? And if you'll notice, this whole piece right here is looking a lot like that whole piece right there. And so you can eliminate this arrow, and on your last line, you get what you need, right? All right, so that is a challenging one. Here is probably the most difficult one. I'm going to have you work on that one by yourself, all right? That's what I'm going to have you do. And so I know this is kind of a lot of information, all right? But basically kind of what I want you to get familiar with in this lecture at least is these things called rules of inference and just what they look like, all right? And especially just make sure you understand this rule, how this works. You got to cite 2 lines. Okay, you always got to cite 2 lines. You cannot just cite 1, and you can only eliminate for a consequent, right? Okay, well that is the lecture. So if you have questions, just shoot me an email or post them in the discussion section, and I will talk to you later.